So when it comes to some other house rules, kindly mute your microphones in order to not disturb our speakers. You can turn off your cameras, but really it is not required. You can also leave them on. And finally, please be as active as you want, meaning that you can leave your questions in the chat box. And at the end of this webinar, we will have a Q&A section. So our experts will be here to answer your questions. Now, to present the agenda. So for those who are watching this recording, let me say again the topic of this webinar. So it is empowering agri-food applications with large language model-based dataset search and integration. Now, we will begin with giving the floor soon to our coordinator of both STELAR and WiseFood, Dimitris Skoutas from the Athena Research Center. He will give an introduction to the STELAR project. After that, Petros, who is also in Athena Research Center, will focus on STELAR with his presentation on augmenting dataset description and discovery in data catalogues. Then again, we will go over to Dimitris to present the WiseFood project, and then we will have our Konstantinos Andrikos from Infili Technologies with his presentations on enriching the descriptions of cooking recipes to support healthy, sustainable, and personalized meal recommendations. And at the end, as I have already said, we will have the Q&A section. Now, let me just admit those who also joined us. I think they're all in the webinar here with us now. Okay, great. So with this, I would stop sharing my screen and I will give the floor to Dimitris.
Thank you very much, Julia, and thank you everybody for joining. Welcome to this webinar. My name is Dimitris Skoutas. I'm a researcher at Athena Research Center, and I'm happy to say that I have the honor to be the coordinator of both projects presenting today. So first of all, what is common for these two projects, besides being coordinated by Athena? Well, the main link, I would say, the main underlying theme is data-driven and AI-driven approaches. So this will be, to a very large extent, what we will be focusing on today in the presentations. And we have complementary use cases. In the case of STELAR, focusing mostly on smart agriculture and food safety, while in the case of WiseFood, focusing on applications directly to citizens for healthy and sustainable diets. So as Julia said, we will start first with a presentation, a short introduction to STELAR, and then a presentation by Petros that will cover into more detail some of the technologies we have been implementing in the project. And then we will switch to WiseFood again with a short introduction and a more detailed presentation. So just give me a second to share the first presentation. Okay, I guess you can see the slides now. So we will start first with the STELAR project. And here you can see some basic information about the project itself. So the full title is Spatiotemporal Linked Data Tools for the Agri-Food Data Space. And this already shows our key two main focus areas, let's say. The one is the data management. So we're building data tools, which directly aligns with the goal that the project is funded in. And also the focus in terms of the piloting activities, which cover use cases in the agri-food data space. The duration of the project is 3 years, and actually we're very close to completion. The project will end at the end of August, so in about a month from now, which means that most of the results are available, and you can find updates in our website, and you can feel free to interact with us if you are interested. And actually next week we also have some more webinars and events showcasing our results. Also here you can see an overview of the consortium. I will not go into details, but briefly speaking, we have 9 partners from several different countries. And there are, let's say, 2 broad categories. There are partners that are focused more on developing the platform and the tools in the project, and also the partners that are leading the piloting activities. Um, so in terms of the challenges, in a nutshell, Stellar aims at making contributions in the data preparation stage of machine learning and AI applications. Data preparation is a very important aspect that is often overlooked. It tends not to receive as much attention compared to building ML models and AI applications, but actually it is a very fundamental part, and to a very large extent also affects or defines the quality of the end results. And it is also a part where data scientists tend to spend a very big portion of their time and often face a lot of challenges. Data preparation involves several stages, typically starting with data discovery, where there are many difficulties, for example, due to the fact that descriptions of data sets might not be very complete or very helpful in order to assess which data are most suitable for a certain task. Then typically, data scientist proceeds with data integration, and this is because usually for a complex task, you need to use data from many different sources, and this will be heterogeneous data. So there is a need to interlink, align, combine, fuse multiple data from different sources and deal with these heterogeneities. And eventually, there is a need to make this data suitable for downstream tasks and for training ML models, which involves challenges like labeling data sets in order to train models, or detecting and mitigating bias, or even using synthetic data generation in cases where real-world data is not sufficient. And to address these challenges, in Stellar, we are building a knowledge lake management system to support fair and AI-ready data. And this has essentially 2 main pillars. On the one hand, the platform itself, which encompasses several core components for publishing and finding datasets and tracking metadata about datasets and workflows. And on the other hand, a toolkit which contains several tools for data description, summarization, linking, alignment, annotation, and documentation, and is extensible. So besides the tools that we are developing in the project, other tools can be added and be used in creating workflows. And the KLMS is pilot tested in several use cases in the agri-food sector, as I will also say in some more words later on. And I have highlighted here these 2 parts because this is the topic that we will cover in the next presentation. So the focus for today's webinar will be on data discovery as far as Stellar is concerned. Regarding the platform itself, the focus here is on tracking metadata about datasets and workflows. And this is important because this is the typical scenario of what a data scientist does, collecting data from different sources and then applying various transformation and integration tasks in which it is typically possible to use to choose between alternative algorithms, alternative models, alternative configurations, and all these decisions have an important impact on the performance both of individual tasks and of the workflow end to end. So it becomes quite complex to track all these parameters and the metrics involved in the tasks and in the executions across a workflow. And this is what the platform, the KLMS platform, facilitates. It collects all this metadata, makes it available through a knowledge graph, and allows a user to compare different executions and in this way to fine-tune the workflow and determine how different configurations impact the results. In terms of the toolkit, as already mentioned, we have a series of tools that address different aspects of the data preparation pipeline. For example, for data discovery, we have data profiling tools. We also have a data summarization engine and a component that can produce an implicit schema for the knowledge graph to facilitate exploration. For interlinking, we have tools for entity and schema matching, for extracting time series out of satellite images and imputing time series to raise the quality of the data, also to fuse the data from different satellite sources and identify correlations. In terms of annotation and augmentation, we have tools for entity extraction, for field segmentation, and crop classification. So as you can see, there is a mixture of both some tools that are general purpose and tools that are use case specific, and all of them can be used in creating workflows to address the use cases of the project, and they can also be extended with additional tools that someone else can add and integrate in the platform. Also, a few words about the pilots. Our first pilot involves use cases related to food safety. Here, for example, one of the main challenges is to extract structured information from texts that are food safety incident reports. For example, identify what was the incident that happened, what was the ingredient that was affected, what was the hazard, and such kind of things. Then in pilot B, we are looking into early crop yield prediction. So the input is primarily satellite data, and we want to identify the crop types and predict the yield both at a local level, for example, for a specific farm, in order to provide advice to the farmer, as well as at a larger scale, like a whole country, in which case it is helpful for providing early warning signals for food security. And last but not least, in the third pilot, we are dealing with use cases in precision agriculture. For example, involving the construction of suitability maps, which again requires to fuse data from many heterogeneous sources, like combining meteorological variables, agroclimatic indices, or soil indices, and so on, in order to identify the suitability of different areas for different crops. And with this, we have concluded the summary of STELAR, and we will continue now with the presentation by Petros, so that will provide more details about data discovery in particular, which is a core part of our platform. So thank you very much.
Okay, thank you, Dimitris, for passing the stage to me. Give me 1 second to share my presentation. Okay, do you see my presentation now, or you see?
Yes.
Okay, then this way. This way is the correct way, right? Okay, nice. So, thank you all for attending. Oh, give me 1 second, sorry. Okay, for attending this presentation. So, in this part, we're going to be talking of how we are augmenting data sets to have a better data catalog in Stellar, and how we are utilizing LLMs for this purpose. We're gonna start with a simple scenario. I want you to get in the shoes of a data scientist who is trying to explore diabetes in this case. If you were this person, you would like to search for some related data sets regarding foods suitable for this diet, or consumption patterns, or effects of foods to diabetics. How would you search such a data set in a data catalog? The answer here is that there are many ways. You could just state your purpose in free text. You could say, I want snacks that are low in sugar and good for people with diabetes. Or you could use alternatively keywords. You could select snacks, low sugar, diabetes. Or you could just give an example of a row of such a dataset that would satisfy your demands. In this case, You can see here a row from a dataset about the nutritional composition of oatmeal cookies, and you could also do it in your own language. The truth is, though, that traditional dataset search interfaces cannot appropriately handle all these requests, especially everything that is not keyword oriented, so natural language queries or examples are not handled appropriately. And this is because they fail to capture the user's intent in this query. So, what are the main issues? The main issues is that they focus a lot on keywords, but the reality is that keywords might mismatch a lot of times. They fail to capture the inconsistency between the description of data sets and the user queries. So imagine when an expert uploads a data set, they know exactly the terminology to use, they know exactly how to explain in detail what is this specific resource that they're uploading. But the truth is that when you're searching, most of the times you don't have such a clear picture in your mind if you're not an expert. And then in the bigger picture, they're just trying to map somehow your query to something that's existing, but they don't try to actually understand what you are searching for or what a possible dataset could satisfy. And finally, multilinguality, which is an aspect very strong in Europe, is something that they don't handle out of the box. So if you see on the right of the presentation, imagine you're using the query I want snacks that are low in sugar and good for people with diabetes. Kind of complete for your purpose. The truth is that data sets that I have on the right, for example, glycemic index of common processed foods, a very valuable data set in your case, it would fail to be retrieved because it has no matching keywords with what you actually submitted. Same applies for the rest two datasets just because they don't have common keywords or they're in Greek. What's more, you could get some false results just because a word like sugar matches in this case. So what we're trying to build, we're trying to build a search interface that overcomes these barriers, that allows users to submit their queries in any format they want and in any level of detail in their expression and fetch the ideal results. And our goal is to actually enable non-expert users who cannot precisely define their desired search results, or they just want to explore a data catalog, overcome this expression barrier and have access to open data sets. How we're planning, we are actually doing it is by using LLMs to analyze the user queries and analyze data sets and define exactly what the users are searching for and what these data sets can satisfy. Uh, the pipeline is clearer here, probably. This is the pipeline we're using in some simple words. So we start from a data publisher that uploads a data set along with a small description of this data set. Then we're using LLMs to fully analyze and understand these data sets and its description and actually decompose it into three features: the general description of the data set, some use cases, and the domain of the data set. These are very useful for us to then um, find the ideal match between the user query and the data set. However, to retrieve candidates, we need to calculate some distance. We need some vectors. So what we do is that we embed these three descriptions that we're creating and we're storing them in a vector database. Then every time a user submits a query in any possible format that they want or any language that they want, we take some extra time to analyze this query and understand um, what this user is searching for in terms of an ideal dataset uh, consisting of general description, use cases, and domain. We then use these feature descriptions to retrieve candidates from the vector database we previously created based on distance calculation. Doing a simple example regarding this, Here we have the example of a meteorological data set about the city of Athens. You see that we have a title and a description that says some general things about how data were collected. What we are doing is actually we're using open source LLMs to analyze first the the metadata that we have and the dataset itself to figure out and other information that could be important for the user. In this case, here in the intermediary analysis, we found out that the dataset includes daily measurements such as temperature, humidity, wind speed, and precipitation. These data, although they were not part of the official description, they are very important to help us recommend the ideal to help us actually search this dataset later on. Then we transform it and we end up with a final output being a general description, which is a combination of what we knew from the dataset from its official description and what we found out with our analysis, some use cases or purpose that this dataset could be used, and the general domain and that this dataset applies. Then we follow a similar process actually for our queries. So every time the user submits a query, you see here you could search for this dataset actually in various ways. Again, you could say I want a dataset to perform weather prediction in the city of Athens, or just weather Athens, or Athens and a date. So what we are using again is we are using open source LLMs and actually the same LLM that we used for the previous step to have the least possible expression difference to create again three feature descriptions. So the general description, a dataset containing weather information about the city of Athens. The dataset may contain temperature and humidity measurements, the use case, and the domain. In this way, you see that if we try to map the initial request of the user to the initial description of the dataset, there might be a mismatch here. It's not always trivial to find the ideal candidates. However, in the second case, when we have transformed this into this coherent description in the three features, it's way clearer both for a user but also for a vector distance function to fetch the ideal results. Here you see overall the architecture that we are using, the steps we talked about before, but also the technologies used for them. As I told you, we're utilizing open source LLMs. We are serving them through Olama, which is a service to serve open source LLMs locally or on cloud. And we're using open source because first of all we believe in the power of open source LLMs, and also because of the fact that our task is simply enough to be solved by smaller LLMs. So this means that given that it's also an online tasks performed at search, we don't want extreme computational resources to run it. We have a ChromaDB, which is a vector database used to store the dataset descriptions and to retrieve them during search. And we have packed our whole service in a Docker, and we are actually exposing a fast API that can be used from the users of the app, and also it can be easily integrated to any kind of existing search interface that the users might already have. So this means that we are producing a solution which is agnostic to the current solutions that search vendors are using and can easily accompany their solutions. So just to show you a quick example, a real example that shows why the world needs our solution. In this case, we tried the European Open Data Portal, which is data a data catalog with many open data sets provided by most organizations within the European Union. And we submitted a simple query. I want to figure out how food should be preserved within the EU. So we were searching for some good guidelines or some instructions or some regulation regarding how we should preserve foods within the EU. And the results, I don't know if they're clear enough, but they were a total failure. So the keywords preserved and EU dominated the search, and we ended up having datasets about how to preserve buildings or passages. Nothing to do with the food domain query or the food domain or the food safety domain more specifically. And this was something that we constantly found out when we were testing. These search engines were not able to handle natural language queries and were not able to handle example queries as well, which I don't have here. Now you see what we retrieved when we submitted the same query in a subset of the European Open Data Portal datasets, and what we end up having when we benchmarked it along a traditional keyword search solution. So on the left, you see our result, the first result that came up when we submitted this query. And we have here a dataset talking about statement on storage of apples and pears. And the use case is to provide information on the proper storage methods for apples and pears, likely for agricultural or food industry purposes. This is a good match. We consider it a good match. And on the right of the screen, you can see what the keyword oriented solution fetched for the same query. It, again, it's a complete failure. This dataset has nothing to do with what we want. It's EU estimated agricultural balance sheets. I don't know exactly what was the keyword that dragged it towards this solution, but this result, but it ends up a failure. So, in a nutshell, what we see is that the LLM-based semantic dataset search allows us to capture the semantic contents of a dataset and the semantic needs of a user, and actually match these instead of just keywords or just plain descriptions. And this really captures the essence of what users are trying to express, allowing them to overcome their expression barriers. We are also enabling out-of-the-box multilinguality with this solution. And in the bigger picture, we are actually unlocking open data catalogs for a non-expert audience and fostering this public engagement with the data that exists. They're out there and they're uploaded. But also, we are fostering the exchange between multilingual and multicultural populations within Europe. So this is what we have achieved so far, and what we're actually working on right now is to exploit these rich multi-component descriptions that we're creating to get into data catalog exploration, summarization, and navigation. If you are interested about it, you can find more on our GitHub page at stellar-eu semantic dataset search, where we will be constantly uploading more and more work as we go on. So that was it with the semantic dataset search. I think we're gonna have a Q&A in the end, so keep your questions for then. And thank you very much.
Thank you very much, Petros. Now we go back to Dimitris to present WiseFood.
Thank you very much. We will switch now to the part about WiseFood. Just give me a second to share the presentation. So again, I will start with a short introduction about the project. Let me just give me a second. And then we will have a more detailed presentation by Konstantinos from Infili. So the WiseFood is a project about leveraging data and AI, which is again the common thing between the two projects that we are discussing today. But in this case, towards empowering citizens to make healthier and more sustainable food choices. So here we have applications that are more directly oriented to consumers. And essentially, we're talking about food recommendations, to put it simply. Again, it's a 3-year project, but in this case, it is actually a new project that started relatively recently in January 2025. So we're in the first 7 months of the project. And again, you can find here the website if you're interested to follow us and get updated with more results as we are moving along in our activities. Also here, a few words about the consortium. Again, we have a consortium with 9 partners from different countries, and there are both partners with computer science background that are focused on developing the applications, as we will discuss later on, and partners from the domain of nutrition and the agri-food sector that have the task to lead the living lab activities and co-design and evaluate the applications. So in terms of motivation, I think this is relatively easy to motivate because our choices, our food choices about our diets directly relate to our health. I believe that this is something that more or less people know, but then in our everyday life, we probably tend not to think too much about it. But there are numerous studies that show that our dietary choices affect directly our health in terms of chronic diseases um, like cardiovascular diseases or cancers, and they are linked to various problems like obesity. Also, there are problems about people being underweight or malnourished, and of course, issues about food waste. So there are many things that indicate that our current food choices are definitely not optimal. And the question is what we can do about it to improve these choices that we make essentially every day in our lives, mostly subconsciously. Um, the vision here in the project is to support citizens to shift towards dietary habits that are healthier and more sustainable. And our perspective is that in order to achieve this, there are 2 main types of barriers that need to be removed or at least lowered. On the one hand, we have knowledge barriers. So making better decisions requires people to be well informed, so to have access to reliable information, um, which is not very easily the case because, for example, here in this domain, of course, there is a lot of information like scientific studies, dietary guidelines, and so on. But this might not always be in a language that is very easily accessible to the average citizen. And more generally, often we have to cope with various issues like information overload. There is too much information from many sources, and people just don't have the time to go through everything and stay up to date. There is fragmentation because information might be scattered in many different sources, and again, it takes time and effort to combine all the pieces and have a coherent view, and also misinformation because not all the sources are reliable. Um, on the other hand, there are action barriers because even if someone is well informed and in principle knows what is, let's say, a good choice, still there might be other factors that prevent us from following these choices in practice. For example, it might be difficult to come up with a meal planning that adheres well to healthy dietary habits and sustainability indicators. Um, it might be time consuming, it might be costly, or it might be that our perception is that such kind of choices would have a higher cost and higher effort. And this is probably why sometimes we're not going towards such choices. Um, so WiseFood is aiming at making contributions along these lines, specifically by leveraging AI to develop what we can consider as a co-pilot, essentially, that will make it easier for citizens to shift towards such healthier and more sustainable habits by providing personalized and up-to-date information, so removing information barriers, and also providing personalized and evidence-based recommendations in terms of cooking recipes and household level meal plans that will make it easier to citizens to follow such habits, make it less time consuming to do such kind of planning on their own and have recommendations that they can easily follow. From a technical perspective, our emphasis is on leveraging generative AI technologies like LLMs, which are disrupting many domains currently, and they have shown very good results in many applications. So it is quite interesting to examine how the application of LLMs can offer new solutions in this area as well. And combine this, of course, with a multi-actor approach because it is very important to take into consideration the perspective of the citizens and also the professionals in this domain in order to ensure that the solutions that we are building are relevant and well aligned with the needs and the goals of and the barriers that might exist from the users' perspectives. So in terms of the applications that we are developing in the project, specifically, we will develop 3 applications. The first is named Food Scholar, and the emphasis here is on the information aspect. Particularly, what this application will do is to collect information from several authoritative and reliable sources, like national dietary guides or scientific articles and so on. Extract this information, summarize it, organize it, and provide question answering capabilities in order to make it easier for someone, for an average user, to find answers to questions that they might have. Then the second application is Recipe Wrangler, which is actually the one that we will be looking into in the next presentation. And here the focus is on cooking recipes. What we're trying to address here is how to enrich the information of recipes in order to support decision making by users. So, for example, given a recipe that has a list of ingredients and some instructions, to provide additional information about nutrition scores, sustainability scores, estimations about time and cost, and these kind of things. So, enriching this profile of a recipe so that it can be used for decision making eventually. And the third application is FoodChat, which uses information from the other 2 applications in order to provide holistic and actionable meal plans, both at an individual level and at a household level, so that people get recommendations about an entire plan and then save time by making individual choices and looking into individual recipes and so on. And as I said, the focus for the next presentation will be on Recipe Wrangler, so you will see more details about that. Also some more details about the applications. This can be used both independently, so the user can interact with each application directly, for example, directly with Food Scholar to ask questions, or with Recipe Wrangler to get to search for recipes, or with FoodChat to get recommendations. But under the hood, these applications are tightly related to each other, and they provide information to each other. So there is a flow of data coming, for example, from Food Scholar to Recipe Wrangler, then from Recipe Wrangler to FoodChat. So essentially underneath there is a platform that manages users, manages the data and the models and agents, and orchestrates these interactions between the applications. And I will conclude with a few words about the living labs, just very briefly. The role of the living labs in the project is apparently very important because we need to co-design and evaluate the applications. For this purpose, we have established living labs in 3 countries, Ireland, Hungary, and Slovenia. The goal here there is to achieve, to ensure diversity in terms of various criteria like cultural backgrounds, seasonality, different dietary recommendations, composition tables, and so on, and be able to evaluate our solutions in regions with different profiles. And in terms of the methodology, the process is structured in 2 stages, where in the first stage, the goal is to co-design the applications, so to get requirements and feedback from the users in order to um, privatized features, for example, in the applications. And then this will be followed by an evaluation phase where the applications will be tested by real users in order to get feedback and improve the results and have another iteration towards finalizing the solutions. So with this, I will end the summary for the project, and I will give the floor to Konstantinos to present Recipe Wrangler in more detail. Thank you very much.
Thank you, Dimitris. Hello, everyone. Let me share my screen a moment. Okay, so now I guess you see my presentation. Okay.
Yes.
So, thanks, first of all, for inviting this webinar. It's very interesting hearing both projects' approaches. So, for this presentation, I will talk about how we are building a digital tool to enrich a cooking recipe catalog with indicators regarding healthy, sustainable, and personalized meal to support personalized meal recommendations. To begin with, it is very well stated in the previous presentation by Dimitris, some of the very common issues that we face with our current food systems, such as is the information overload, with the citizens struggle to find reliable food information in a vast pool of information. Of course, as we all are aware of, our current food systems are major contributors to environmental pollution. We also have issues with the lack of reliable sources and rich sources for digital recipe collections that do not include indicators for nutrition or environmental impact, or indicators for the cost and the preparation effort that is needed. And also, even if someone wants to adapt a healthier food habit and more sustainable habit, they are often constrained by these issues and constraints like budget or preparation time. The goal that we are trying to reach within the WiseFood, and more particular with the Recipe Wrangler tool that we are building to address those issues, we want to empower citizens to adopt healthier and more sustainable food choices. And to that end, we are building a tool that for a given recipe creates the so-called recipe profile, which is actually provides indicators for the nutritional and the sustainability impact these recipes have. A very important feature of this application we are designing and building is to allow the user to compare two or more recipes in terms of these indicators: nutritional sustainability, cost, or preparation time, but also enable users to perform ingredient substitution for a given recipe to gain a more eco-friendly or a more nutritional final recipe. And of course, all these functionalities have to be under the umbrella of transparency and trust between the application and the user. So we need to output the sources that were used in order to perform those calculations, or the data where those data came from, some reliable sources. So this is also a very important aspect. An overview of this application, high-level architecture of the application. As already been said, we are utilizing language models for the user to interact with the application. So what an LLM agent actually is an AI system that can take a user query, reflect on the query, reason on that query, and plan the execution that will be needed in order to provide back the user with a response to fulfill the user requests. Basically, an LLM agent acts as the cognitive brain of the application that will the main aspect would be to understand and invoke the tools that are needed to perform certain calculations, such as accessing the databases, perform several other calculations, processing steps, etc., in order to return a meaningful response back to the user. And for this, the recipe wrangler application up to date, we have developed two tools. That one is for searching recipes within the database, and another tool for profiling a certain recipe, meaning analyzing the recipe to return full nutritional sustainability data. Let's dive in more in detail. First of all, the first issue that we are facing when building such application is the data. What kind of data are we going to use in order to process and have our data lake, let's say. So to this end, we have used a very well-known dataset within the domain, which is the Humus dataset. It consists of over 500,000 recipes from food.com mostly. This raw data format is simple Excel files. It's a table format structured in rows and columns. And one of the very first steps for processing those data was to create some semantic relationships that will be utilized by the large language model agent. In the raw data, there are no relationships between ingredients, methods used for recipes or cuisine or dietary patterns. So we needed to reform this information we had and to create such semantic relationships. So to that end, it's very common practice to form our data into knowledge graphs. That is very popular also format for applications with LLMs. Very briefly, a knowledge graph is actually a network of interconnected entities, such as one entity could be a recipe that is related with other entities that represent ingredients via a meaningful relationship, such as has ingredient for that case, or could be connected with other nodes, such as tags for representing a recipe that is in Asian cuisine or vegetarian, or you name it, actually, whatever this tag could be. So having this step performed, we now have a rich contextual understanding beyond flat tables, such as was the case in the raw dataset. And as I said, yes, this format helps very much the machine to understand the LLM agent, but also it is easily understandable by humans. One step further to that end, for the forming our knowledge graph in a way that can be further be utilized was to perform some similarity and match certain nodes. This actually sets the basis for when we want to substitute an ingredient for a given recipe. So how could we give this information to an LLM? We need to have some connections between the ingredients. And this was done by taking first the raw text for an ingredient. We are using a so-called bending model, which actually takes the text and transforms it into a sequence of numbers. It creates a vector, and this is done for every ingredient within the graph. And then by a simple, relatively simple comparison, we see how much similar is the vector for one ingredient to a vector for another ingredient. And if this similarity is above a threshold that we can set, this similar to, in this example, relationship is being created. So we have, in this way, further enriched the similarity, the semantic similarities between different nodes and within our knowledge graph. In a similar manner, we create embeddings for the recipe level, but this time not for the ingredients as in this previous slide. This technically has some differences with the previous method used because we are now using an embedding model within the host of the knowledge graph. So we again perform the same similarity. We again perform the same vectorization actually for the recipes, and by similar comparisons, we can get similar recipes for a given one. And then the next slides, I do have some examples that highlight some of these functionalities. For example, for a simple recipe search, a user could enter a query like tell me a recipe with spinach and chicken, and there are two tags in this case. The user has selected to be under 1 hour and a recipe with a high protein. So the output of the model is something similar to this, has been structured in a way that the user can understand with full indicators about protein, calories, all the ingredients, the servings, and the instructions finally. Another example is to how we can get nutritional sustainability insights for a given recipe. So, for example, if a user pastes a raw recipe he has found online or in another source and has not any kind of information for that recipe, the model invokes the appropriate tools that perform this kind of calculations, and we get an output similar to this one with the total energy of the two serves. In this case, the protein, fat, the carbohydrates, and sustainability indicator. And also very important to highlight is that we also need to output the source these data were extracted from and the calculations that were done. And finally, as I said, we also have the functionality to compare some recipes. So for given two recipes, I want a comparison in terms of nutrition and sustainability. This is actually the same tool that is being invoked, but we can have the output of the model structured in a way that clearly indicates the comparison between those two recipes for the terms of nutrition and sustainability. So yes, a small summary text would be generated in that case that let the users know about this comparison. So that was all from my side. I'm sure there are questions, so I'll be happy to discuss in the next session. Thank you.
Okay, thank you very much, Konstantinos, and thank you very much to the rest of our speakers. And indeed, as Konstantinos has said, we will now move on to the Q&A portion of our webinar. I did notice that we have one question in chat. Now let me see if I can read it while I'm sharing my screen. So, how much is there a human in the loop approach in the data discovery process? This question was posed by Anna. So, since it's referring to data discovery process, Petros, I think this is aimed at you.
Yes, thank you very much, Julia. So, yeah, Anna, the answer here is the fact that it's not actually human in the loop, it's like human centric. So, uh, it's not planned at this point. The search actually interface is not an interface where you have a discussion to end up having a data set. So, after the first query that you're using, you're not actually giving feedback on this query to reach to the dataset you want. Although this is like a very interesting approach, it's human centric because it allows the human to give the initial guidelines, let's say, to what they're searching for, and it expands on them to fetch them to get them into the structure we want to have an efficient and optimal search. But yeah, at this point, the search does not have human in the loop. However, all the extensions we have planned when it comes to exploration of the data catalog, or summaries of the data catalog, and navigation in the data catalog, there it's like human in the loop comes into play actually, as you correctly mentioned.
Also, if I may add, because it's indeed a very interesting question, we could add such kind of features also in the data profiling part. So when someone is publishing a dataset or profiling a dataset, then you could have a human check the augmentation that happens by the LLM and perhaps validate it, or maybe steer the profiling process to focus on certain features and so on. So this is something that indeed would make sense as an extension.
Okay, thank you both. So, in the meantime, we got one more. It's from Oliveira. Okay, thank you for the great presentations. Are the three WiseFood applications using data sets in English, or are they in multiple languages? Dimitris, I think that maybe this question is aimed at you.
Well, in general, yes, we have the raw data that we're collecting are in different languages. For example, we are facing this kind of issues when collecting national dietary guides or food composition tables. And again, there we're relying on the capabilities of certain LLMs that can process multilingual content uh, and transform the data. Um, it's up to discussion whether the output will also be in the original language or in English. At the moment, for the development, we're focusing on English, but definitely this is something that inherently has to have multilingual support.
Okay, thank you very much, Dimitris. So, of course, if somebody else wants to pose a question, you can also unmute yourself and pose a question if you feel more comfortable that way. we can wait a bit to see if there will be somebody else popping up to ask something. But in the meantime, I would just want to share quickly, as Dimitris has said, the STELAR project is wrapping up very, very soon. Actually at the end of August, and yes, we do have more events lined up, and I just wanted to share very quickly an overlook of I think that you can see the picture here of the upcoming events. Of course, here you can see the WiseFood and STELAR webinar that is happening as we speak. But apart from that, please feel free to join us on July 23rd, that's next Wednesday, for STELAR's final event. We will actually have a walkthrough and demonstration of the STELAR KLMS. And also the next day, we will be joining our forces with another project, Cracksense. The title is From Orchards to Orbits, Sensing Strategies in Agriculture. So as you see, the focus will be quite different than from this webinar. All of the registration links can be found on STELAR's LinkedIn page. So we do hope to see you there, because of course we will have a Q&A session there as well. So if you want to ask something else that is maybe not in the scope of this webinar, that would be a great opportunity. And with that, I would like to thank you all for joining us, and have a nice weekend. And thank you to all of our speakers once more.
Thank you, Julia, and thank you all very much for joining.
Thanks everyone very much. Thank you.
Thank you, everyone.